Okay, ladies and gentlemen, welcome back, and this is P-Dog with Chapter 19 lecture on acids and bases. So let's get started. We're going to try something a little different this time. We're going to edit in some other video in with this one, and hopefully it'll help you understand this a little better. Okay, so we're going to start with the properties of acids. They are aqueous solutions, with most having a higher hydrogen concentration than hydroxide. Okay, acids are sour if they're tasted. They produce hydrogen in their reaction with metals. And they look like water, and they are electrolytic solutions. Weakly acidic solutions feel like water on the skin, except when there's an open cut. In other words, it stings. And imagine getting lemon juice on a paper cut. And then they're neutralized by bases to produce a salt and water. So the first thing we're going to do is show you how a metal would actually produce hydrogen when it reacts with water, or how an acid produces hydrogen when it reacts with metals.
Okay, so here is how an acid is going to produce hydrogen when it reacts with metals. So we're going to put, sorry, not hydrogen here, an acid is going to do this. So we'll take hydrogen chloride and we will mix it with, let's put some aluminum in with it, Al. Okay, well, this happens, and this is going to produce, the H is going to, or the aluminum is going to get in with the acid, and it will cause the chlorine and hydrogen to split to make H plus and Cl minus. And in doing that, it is also going to strip electrons because our H plus over here does not have enough. And so these electrons will hook up with the H plus, and we'll get AlCl3, because that's the ion that aluminum is going to make, and every aluminum will lose 3 electrons. And it will also produce hydrogen gas. And then once this is done, then we need to balance what we're doing here. And this actually winds up being, we will get 6 hydrogen chlorides and 2 aluminums to give us 2 AlCl3 and 3 H2s. And here is your hydrogen gas.
Some common acids that we come across when we're dealing with them. There's HCl, which is hydrochloric acid, and that is your stomach acid produces that, or it's also the muriatic acid that you put in your swimming pool. We also have sulfuric acid, which is excellent for dissolving bone. Nitric acid, which also causes severe burns if you get it on you. Phosphoric acid, which is actually really important biologically. If you get rid of those H's, that PO4 is the phosphate that we use in ATP. So that's another, that's an important ion right there. And then we have acetic acid, which most of you may have heard of when it is wine that has turned sour. And so wine that has turned sour, well, if you take that in French, vin is French for wine, and sour is egg, and so together they make vinegar. Okay, and that brings us to the properties of bases. Bases are the opposite of acids in some ways, and they're similar in others. Bases are aqueous solutions, with most having a higher hydroxide concentration than hydrogen. They are bitter if they're tasted, and they look like water, and they look like water. They are also electrolytic solutions. Now, basic solutions feel smooth and slippery to the touch. For example, soap is a base, and it feels very slippery to the touch. And it will do that even if it is in the eyes. That's some typo that I have in there, so don't worry about that. It does sting. And bases are also caustic. They dissolve tissues. And that's why, for example, sodium hydroxide is a drain cleaner, because what do you usually have clogging your drains? Hair and other tissue stuff. So that's why it is effective for using that. Okay, we use indicators when we're dealing with acids and bases, because those are substances that change colors at different concentrations of hydrogen. So for example, litmus is red in acid and blue in bases. And I have a way for you to remember that. For acid, you have litmus paper turning red, and for bases, you have litmus paper turning blue. And so this is the mnemonic I have for litmus paper, is that acid turns litmus paper red and bases turn litmus paper blue. Alright, another indicator we have is called phenolphthalein, and it is colorless in acid and neutral solutions, but it turns pink when it becomes basic. There is a universal indicator, which is a mixture of a whole bunch of different indicators, and it is a rainbow of colors. It is red when a solution is very acidic, to dark blue when it is very basic. When acids and bases mix, they have what's called a neutralization reaction, and it is a special kind of double replacement reaction, where one of the anions is a hydrogen, and the other cation, the cation of the other chemical, is hydroxide. So for example, hydrogen chloride plus sodium hydroxide go through a double replacement reaction where the sodium attracts to the chlorine and the hydrogen attracts to the hydroxide, and we get NaCl plus H2O. There's your salt, and that is your water. Now we have three primary definitions for how we determine an acid or a base. The first one is the Arrhenius definition, and you'll need to know all three of these and how they define an acid or a base. The first one is the Arrhenius definition, and that is for acids. It is a substance. They are substances that dissociate in water to produce hydrogen ion. Now bases are substances that dissociate in water to produce hydroxide ion. Again, when we talk about dissociation, it is the breaking apart of a substance into positive and negative ions by reaction of the substance with water. Okay, now water itself has its own dissociation, and we're going to talk about that right now. Okay, now an interesting thing about that hydrogen that goes over with the water is that also fits into the Bronsted-Lowry definition. Because an acid then is any substance that can donate a proton. Well, a proton is that H plus that traveled over to the other water. And a base is any substance that can accept protons. So, the other water molecule that didn't give up the hydrogen actually accepted a hydrogen, and that became So in that case, it was a base. So you can see how the hydrogens going back and forth can turn water into both an acid and a base, and we're going to get into that in a minute. Okay, then we have what's called a Lewis acid or a base, and it is any substance that is an electron pair acceptor for a hydrogen. So if it has a lone pair sitting out there, the hydrogen can, or any positively charged thing, can attach itself to that electron pair. If you have the electron pair, you would be the acid. And, I'm sorry, if you accept the electron pair, if you take it from someone else, you're the acid. And if you donate the electron pair, then you are a base. And those are our three definitions: the Arrhenius definition, the Bronsted-Lowry definition, and the Lewis definition. Now, that H3O plus is the hydronium ion from that other video, and H plus is really a shorthand version that really represents H3O plus. That there are no lone H pluses sitting out there in the water. They are only out there because of the attraction to the negative end of the oxygen, or because they are that attraction to the negative end of the oxygen in the water is attractive to the hydrogens in acids. Now, this brings us to the different kinds of strong acids and bases. And these are so strong acids. Now, pay close attention to our difference here. We're talking about strong acids and bases versus weak acids and bases. This is different from concentrated and dilute. So, strong acids and bases will completely dissociate 100% in water. They are strong electrolytes. That means they conduct electricity very well, and they're highly acidic. And one way that you can tell that it is a strong acid is when their dissociation is written out in an equation. So these guys are HCl plus H2O will make H3O plus and Cl minus. But this is one direction. It only goes one way. Hydrochloric acid in water will completely dissociate to make the hydronium and the chloride, so that the original concentration of the HCl is equal to the concentration of your acid that you're going to have afterward. This is to separate it from weak acids, which do not dissociate completely. They are weak electrolytes, which means they don't conduct electricity very well, and they are weakly acidic. So hydrogen fluoride here is another example of this. Hydrogen fluoride, when it's put into water, will also make hydronium and fluoride ion. However, it does this in a reversible way, and so we will create an equilibrium situation with our dissociation, and we create what's called a Ka. Okay, and our Ka, it would be our equilibrium constant for an acid. Okay, strong bases do very much the same thing. They will dissociate completely. They are highly basic, and they are strong electrolytes, and they will separate into their metal, their hydroxide, and their water. Okay, weak bases are those that do not dissociate completely, and they're weak electrolytes, and they're weakly basic. For example, ammonia and carbonate, and I believe this is hydrazine, H2N2H2, is another weak base. When acids and bases dissociate in the water, they create what's called a conjugate pair. In acids and bases, all acids and bases have a conjugate pair that go with them. It is just like the conjugate pair in a math problem. So where you have, say, 3 over 2x. I'm sorry, 3 over 2 minus the square root of x, and you need to rationalize the denominator. You're going to multiply this by 2 plus root x and 2 plus root x to get rid of, and these become a difference of squares combination. So this is a 4 minus x on the bottom and 6 plus 3 root x on the top, but your denominator is now rationalized. So then you can figure out what you have on top. That you no longer have the radical on the bottom, and you can, and this is the proper way to write fractions. Well, acids and bases also have conjugates. And when they dissociate, they'll have these other partners. So the conjugate base of an acid, so you put an acid in, and when it dissociates, it creates its conjugate base. And that is a substance with one less hydrogen than its parent acid. Now, when you put a base into water, it will dissociate to create a pair for it. That will have one more proton than its parent's base, and it is also its pair. So, for example, here you're going to have an acid and a conjugate base, and here you would have a base and its conjugate acid. That the water will gain a proton, okay, and when it gains a proton, it is a base, and this over here is its acid. This carbonate, or this HCl3 will lose a proton to look like carbonate, which would make this an acid, and this a conjugate base. So, if HCO3 is an acid, its conjugate base is going to be CO3 minus. If H2O is a base, its conjugate acid would be the H3O plus, the hydronium. Now, there are some substances that can do both, and these are called amphoteric. They are a substance capable of behaving as an acid or as a base depending on their conditions. For example, water has both hydrogen and hydroxide, and so can behave as an acid or a base depending on what it's acting with. And that brings us to the properties of water and how we measure the strengths of acids and bases. In pure water, both hydroxide and hydronium have a concentration of 1 times 10 to the negative 7th molar. That is what makes water neutral. It is the balance between these two ions. The equilibrium constant for water, Kw, in all acid-base solutions is calculated by the following equation. Kw equals hydronium concentration times the hydroxide concentration equals 1 times 10, and that should be to the negative 14th. Negative 14. Okay, and here's how we get it.
Remember, the dissociation of water is H2O plus another H2O is in equilibrium with making hydronium and making hydroxide. So, once we have our dissociation equation out there, we notice that it is an equilibrium reaction. And so with every equilibrium reaction, we can have a equilibrium constant. And our equilibrium constant in this case is known as Kw because it is the equilibrium constant for water. And it is going to equal, and we'll build this just the way we do any other equilibrium constant. It is the concentration of one product times the concentration of the other product divided by the concentration of the reactants. However, water is a liquid. And because water is a liquid, it doesn't count in our equation. And because it doesn't count in the equation, we then just have a new Kw of the concentration of our hydronium times the concentration of the hydroxide, and that produces a Kw of 1 times 10 to the negative 14th.
So when the hydronium ion concentration increases, that means we've added acid to our stuff. And the hydroxide ion has to decrease because this 10 to the negative 14th is a constant. It doesn't change. And so if one part of it goes up, the other one's going to go down in order to maintain our 10 to the negative 14th constant. So any solution then with a hydronium ion concentration greater than 1 times 10 to the negative 7th is acidic, and any one with a concentration less is basic. Now the way we can measure this is by paying attention to what's called the pOH. Concentrations of hydronium can be measured directly to determine how acidic or basic a solution may be. Or we can use the pH scale as a simple alternative. pH scale, the pH scales and pOH scales are logarithmic scales. The hydronium can be slightly higher than 1 times 10 to the negative 1 molar, or as small as 1 times 10 to the negative 14th molar. A scale must be used then to represent very high and very low concentrations on a graph. We do that with a logarithmic scale. So, pH, every time the hydronium concentration increases by a factor of 10, or 10 to the first, the pH goes down by 1. So as we increase by 10 to the first, the pH goes down by 1. When the hydronium concentration increases by 10 squared, okay, or by 2 factors of 10, the pH goes down by 2. 2 factors of 10, of course, being 100. So water's hydronium concentration, just for being there, is 1 times 10 to the 7th, and so it is a pH of 7. If the hydronium concentration increases by adding an acid, then let's say it increases to 10 to the negative 4th molar, then the pH will increase to, the pH will decrease to a pH of 4. If the hydronium goes up to 10 to the negative 3rd, the pH decreases to 3. If it goes up to negative 2, it goes to 2. If it decreases to 10 times 10 to the negative 12th, then the pH becomes 12. And so here's how we calculate it. The pH is the negative log of the hydrogen ion concentration. Okay, but here's how we figure out
Our
logs.
pH formula gives us negative log, there's that funny glitch in my iPad screen again, negative log of the hydronium concentration. Well, we have hydronium concentrations of, it can be, let's see, it can be 1 times 10 to the negative, call it 5th molar. Well, if that's our hydronium concentration, then what this really does is we'll find this pH. The pH is going to equal the negative log of 1 times 10 to the negative 5th molar. But here's how we figure it out. If you remember that this exponent comes out in front of the log, by our log rules. So this becomes negative times negative 5 log of what's left over there is 10. Well, that negative times a negative becomes a positive, so that becomes 5 log of 10. And since the log of 10 equals 1, the pH of something of 1 times 10 to the negative fifth, the pH of this will become simply 5.
Okay, so that's how we calculate our pH. And you can do the same thing with pOH, except you do the same calculation with the hydroxide concentration. But the curious thing about this is that they always, the pH and the pOH, because the Kw equals 1 times 10 to the negative 14th, that if you add the pH and the pOH, it always adds up to 14. Now the way we measure it is we use indicators to change colors within a specific predicted pH range. Phenolphthalein, for example, changes from colorless to pink in a pH range of 7 to 9. Now, pH indicator papers, such as litmus and Alkacid, have indicators soaked and dried on them, and they change color at particular pHs. And pH probes are really the most precise method to use, but they're more expensive and they require some skill to use them. Okay, and then we have a different classification of substances, and this uses acid-base properties to maintain a steady pH solution. Okay, and these mixtures can either absorb or release hydronium ions in order to keep a solution's pH stable. And they are made by mixing conjugate acid and base pairs. So that is it for Chapter 17. It's P-Dog signing off.